Hi everyone, this is the second video for 5-3 solving trig equations. If you didn't watch part 1, make sure you go back and watch part 1 before you watch this video because part 1's a little bit more informative on what we're doing with solving trig equations, and this video just takes it one step further and provides some more examples. So let's look at representing our answer a different way than what we saw in the first video. So in part 1, we talked about solving trig equations, and all the trig equations that we solved, the answers were found within a distinct interval of either 0 degrees to 360 degrees or 0 radians to 2 pi radians. So we were always restricting our solutions to be within one revolution of the unit circle. In this case, we are going to look at solving for all real values now. So when we're solving a trig equation, unless stated otherwise, unless given an interval, we're going to assume that we're solving for all real values. So due to the periodic nature of the trig functions, meaning that they repeat every so often, every period, there are going to be multiple solutions to the trig equations. And so in order to represent all of those solutions, we use the following notation. So for sine and cosine functions, they repeat every 2 pi. That's the period of sine and cosine. And so in order to represent an answer for all real values, we're going to put what our angle measure is there, for example, pi over 4, and then we'll put plus 2 pi n, where n is just any integer value, kind of taking into account multiple revolutions of the unit circle or multiple iterations of that period. Okay, so for sine and cosine, we're going to be using 2 pi n. For tangent, if you recall, tangent has a period of just pi. And so when we're representing all real values for tangent, we're going to take whatever our angle measure is, and then we're just going to put at the end plus pi n to take into account multiple iterations of that period of pi for tangent. These answers also work for their reciprocals. So if you're looking at secant and cosecant, it would also be using 2 pi n, and if you're looking at cotangent, it would also be using pi. Okay, so let's do a couple examples. So first one, we're going to solve 3 tangent squared of x minus 1 equaling 0. And notice they don't give us an interval, so it is going to be assumed that we're going to represent our answer with all real values when we express our answer. So I'm going to start by getting tangent isolated. So I'm going to add 1 to both sides, and I get 3 tangent squared of x equals positive 1. Then I'm going to divide by 3, and tangent squared of x equals 1/3. And this is tangent squared. I just want tangent, so to get rid of the squared part, I'm going to take the square root on both sides, and you want to make sure when you take the square root that you include that plus or minus. So I end up just with tangent of x on the left hand side equal to plus or minus square root of 1/3. Let's simplify that square root of 1/3. When you take the square root of a fraction, remember it is taking the square root of the numerator and denominator separately. Square root of 1 is 1. Square root of 3. Rationalize it. So I actually have plus or minus square root of 3 over 3. So I'm looking at where is tangent of x equal to positive or negative square root of 3 over 3. Okay, so let's start in quadrant 1. In quadrant 1, tangent is square root of 3 over 3 at pi over 6. So I'm going to write pi over 6 to take into account all real solutions. I'm going to put plus pi n. So that's the only difference here, is we're putting that plus pi n at the end, and it is pi because I'm working with tangent. In quadrant 2, tangent is equal to negative square root of 3 over 3 at 5 pi over 6. and then we're going to put plus pi n at the end. And I don't even need to worry about quadrant 3 and quadrant 4 because it's already taken care of here since tangent repeats every half unit circle or every pi radians. So those are my two solutions showing all real values. Next example. So we have 2 cosine squared of x equals cosine of x. Again, we're going to represent our answer with all real values. This one, so I have a cosine squared, I have a regular cosine. I'm going to have to factor this. So we want to first start by setting it equal to 0. So I'm going to subtract that cosine of x to the other side. I can't combine these because they're not like terms, but what I can do now is factor out a cosine from both, leaving me with 2 cosine x minus 1 equals 0. And like we saw with the factoring example on video part 1, now I have 2 different factors that I'm going to set equal to 0 and solve. So I have cosine of x equaling 0, which will give me some solutions, and 2 cosine x minus 1 equaling 0, which will give me some other solutions. So on the unit circle, cosine of x is equal to 0 at pi over 2. Since I'm looking at cosine, I'm going to put plus 2 pi n at the end. And cosine of x is also equal to 0 at 3 pi over 2 plus 2 pi n. So those are my solutions for the first factor in my equation. Now I'm going to solve this one. So if I add 1 first, divide by 2, I get cosine of x equals 1/2. Cosine of x equals 1/2 when x is pi over 3. So it's going to be pi over 3 plus 2 pi n. And cosine of x equals positive 1/2 at 5 pi over 3. So 5 pi over 3 plus 2 pi n. Again, the only difference from video 1 is that now we're putting this plus 2 pi n at the end to account for all real values in which cosine is equal to either positive 1/2 or 0. Okay? All right, here we are going to do something similar to what we did in the last example. We're going to start by getting this set equals to 0 so that we can factor, and hopefully our factors end up being just in terms of one trig function, so that way I can solve this equation. So I'm going to start by subtracting that 2 cotangent x, get this set equal to 0, and now I'm going to factor out a cotangent of x. That's what both of these terms have in common, leaving me with cosine squared of x minus 2 equals 0. So then I get 2 different factors, and it's good that both of these factors are in terms of only one trig function, which is what we want. We don't want to try to be solving an equation that has 2 different trig functions in it. Okay, so let's look at cotangent of x equaling 0 first. So cotangent of x equaling 0, keeping in mind that cotangent is cosine over sine from those identities. So if you look at your unit circle, you're looking for where cosine is 0, so that way I take 0 over something and get cotangent equal to 0. That's going to be at pi over 2. And since we're working with cotangent, we're going to put plus pi n. And that's the only spot where cotangent is going to be 0 in the first, between 0 and pi. And then let's solve this equation, continue solving this one. So I get cosine squared of x equal to positive 2 take the square root of both sides, and I get cosine of x equals plus or minus square root of 2. This is not a value found on our unit circle. Square root of 2 is going to be outside the range of cosine, and so this is not even going to give me a solution here. So the only solutions is my pi over 2 plus pi n. Okay, and one last example to finish up this lesson. We have 2 cosine squared of theta plus 3 sine of theta minus 3 equals 0. So this one's already set up nicely in order to factor, but unfortunately I have a cosine and a sine. And we did do examples similar to this in Unit 8 when we were factoring trig functions. And if you recall, back to Unit 8, I told you guys, if you want to factor something that looks like this, you have to have the same trig function. So I can't work with a cosine squared and a sine squared. And a sine. I need those to be the same. Okay, so we are going to change this cosine squared of theta using one of our Pythagorean identities that we used last unit. So if you recall from last unit, sine squared theta plus cosine squared theta equals 1. If I rearrange that identity, I can replace cosine squared of theta with 1 minus sine squared theta. That way I created an equation only in terms of one trig function. So let me make that substitution. Okay, now I'm only in terms of sine, which is what I want. Now I'm going to distribute this 2. Okay, and now I'm going to write this as I would want it to be written in order to factor. So putting the sine squared first, so negative 2 sine squared theta plus 3 sine theta, and then combining my constants here, 2 minus 3 is going to give me a negative 1 equal to 0. I don't want this negative out in front, so I'm just going to multiply everything by a negative 1. So I get 2 sine squared theta minus 3 sine of theta plus 1 equals 0. And this ends up like a problem pretty similar to the last problem on video 1. I'm not going to go through how to factor this again. You guys should be pretty proficient at factoring this. Like I said in the last video, change this to x if you need to in order to factor it. But you guys need to know how to factor something like that. So it is going to factor out into 2 sine of theta minus 1 and times sine theta minus 1 equals 0. And so that's going to be my 2 factors. 2 sine theta minus 1 equals 0 and sine theta minus 1 equals 0. So I'm going to solve this quickly. So I get 2 sine theta equals positive 1. Sine theta equals 1/2, and sine is 1/2 at pi over 6 plus 2 pi n, and in quadrant 2, 5 pi over 6 plus 2 pi n, and over here we get sine of theta equals positive 1, and sine is positive 1 at pi over 2 plus 2 pi n. So I have that solution, and I have these 2 solutions for this problem. And that's it for solving trig equations. Let me know if you guys have any questions. Thank you.